start as well. Okay, let's get started. Wow. Are we all at the new building? We're not moved yet. We got 2 more weeks before we move to the new building. But it does seem kind of light today. Maybe the rain's keeping people away. Who knows? All right, so today is actually an important day. So you guys who showed up are going to get all the good stuff, all the good information. So I put out 2 new items on behacker.com. We've got the midterm exam, and we have the CSLO essay that I'm going to talk about in great detail for the first and only time. And then those of you guys who have missed it, who weren't here today, have to watch the video to get this information. The midterm exam we'll be doing 1 month from today, or actually tomorrow. It's due on April 17th, the Sunday after tax weekend, for those of you who file taxes. So, and nobody in here probably files taxes, who knows. It will be due 1 month from today. It will be uploaded into the ITU EMS. Don't look for the links right now. They're not there. They're going to be created this week. It is a take-home midterm exam. The other thing I'm going to go over today in the new posting is the CSLO essay. However, it's nothing like the CSLO essay you've had in the past, so I need to explain that to you as well. That one is not going to be due until the very last day of the course, probably in May 9th, from what I hear. I don't know, people keep saying May 9th, but I don't even know if that's really the last day. I have to look at the calendar. The final exam will be an in-class exam. You must show up for the final exam. You cannot take it remotely. It cannot be, you actually have to physically show here, physically sit down with a piece of paper and a pen and actually write the exam yourself. It will be closed book, closed notes, but the midterm is open book, open notes, open everything. And you have some flexibility on that, and you have a month to turn that in. If you're late on it, it's going to actually be counted late. So it's not a bad idea to turn it in on time. And here's what the midterm is all about. It is 25 points of the total points out of 100 for the course, 25%. And if you could keep it down, that's great. We have 10 questions. Each question is worth 2.5 points. And it's actually kind of straightforward. You're going to write a paragraph or 2 for each one of the questions. When I say a paragraph, I mean 4 or 5 sentences. I don't want you to get carried away with this. Don't write a page for each question is the same as a paragraph in terms of your grading. And it's actually kind of straightforward. Out of all of the midterms I put together, this one's probably the most straightforward, I think, this term. The questions are fairly self-explanatory. They're going from the beginning of the course all the way to week 7, which is today, actually. This is the week 7. So we have, we're halfway through the course, actually. It doesn't seem like it's been that long, but it has, I guess. So as an example, the first question here, what makes software engineering different from other problem solving in other engineering fields and sciences? You can probably use your best judgment, use any type of research you want to do. Do not cut and paste stuff off the internet. I'd rather have you answer the question. In fact, a lot of these questions, you're not going to find one correct answer. It's going to be from your perspective. What do you think this is? And as an example, the second one, how does software engineering deal with complexity in large projects? It's like you can't find an answer for that on the internet. So the best approach is to kind of use your background information, use the lecture slides, use the videos, use everything you can. And know that whatever you're answering, as long as it's appropriate and it meets the question criteria, you're providing a good answer. So, are there any questions about the expectations or anything related to the midterm exam? I'm not going to go through all the questions. I'll leave you for that. If you do have a question about one of the questions, you can send me an email message. I can answer the questions for you. And what's meant by a paragraph, I think it was like 4 or 5 sentences, maybe, the paragraph. Written in English, hopefully, so I can read it. So. Okay. Now the more interesting of the 2 assignments is the CSLO essay. So let's spend a few minutes on that one. In the past, if you're familiar with what we did in the previous terms for this particular class, or actually for all of your classes, not the same. Totally different concept. What do we have? We have 25% of your grade. So actually that's 50% right there with, was that 25? I can't remember if it's 20 or 25. I just looked at it a few minutes ago on the midterm. But it's close. It's like 40 to 50% of your grade is with this midterm exam and also with the CSLO. But the CSLO, is going to be the make or break, essentially. It's 25%, which means if you don't turn it in, you get 75% as your final grade, which is a C+, I believe, which is not really good for a graduate student. So what are you doing for this? You're writing a 3 to 5 page double-spaced essay. And double-spaced, so 3 pages is really a page and a half single-spaced. So I think you can judge it that way. And on a selected topic of one of these 5. So on the bottom here, and I'm going to go through these in a lot more detail, you have 5 questions. You're picking one, selecting one. You're writing a 3 to 5 page essay on it. And you're providing 3 reference citations. So you're probably going to need to do some research. And you can use professional journals, on the internet, to library sources, anything that you have access to. You do actually have student accounts on the San Jose State University Library, so you can use that as well if you know how to get to it. Your research is performed to gather the information for your paper that's used in your paper. Your paper must follow a style format. Style format being either the APA, A as in Apple, P as in Paul, A as in Apple.org, American Psychological Association format, or the MLA, or there's one called the Little Brown Book or something, writing styles. What you're looking for is a professional college-level writing style format that has a title page and page numbers and margins and double-spaced, because you're being graded on the looks of it, how it looks, how it reads, your comprehension of the English language in terms of how you're writing it. It is your own writing, so your own writing cannot contain portions of cut and pasted information from the internet. Unlike the brand new way of writing these days, where people go out to the internet and they cut, paste, change the words around, cut, paste, don't do that for this assignment. Do not do that, because what we're going to do is we're going to take it and we're going to process the papers through turnitin.com and also through a couple of other internet checks for plagiarism. And if it comes back with more than 50% plagiarized, which is easy to do actually if you're cutting and pasting, it'll be 80 to 90% plagiarized at that point, then what ends up happening, actually somewhere between 40 and 50%, will allow a little bit but not the entire paper, because people have a tendency to summarize and paraphrase wrong, and that turns into plagiarism. And then there's some room for error on the tool. If it comes back and it matches some other student's paper in the class, or if it does not have proper reference citations for any work that you've put in there that's not your own writing, you're going to get a 0 on it, and there's absolutely no means of redoing it. You only get one shot to turn it in, so when you turn it in, you have to make sure it's going to pass through plagiarism checks. And it doesn't exist on the internet, nobody else turned it in, so we're not recycling assignments here. If you get a 0 on it, which means you're going to get 75% in the class, which means you're going to get a C+, absolutely no grade change at that point, if that's the case. That's the policy, set in stone, that's what's going to happen. So this is your opportunity to practice your English writing skills in an academic environment for a class, for school, for something that's going to hopefully provide you with some better skills, maybe. After reading through some of the CSLO essays from previous terms, this is definitely an area in which students might need some more practice, essentially. And how does this work with the concept of student learning outcomes? Each one of the 5 here, which you get to pick one of, is based on the student learning outcomes of the course. And what I'm going to do is kind of go through all 5 and tell you what I'm looking for, because it's left to interpretation in some cases, depending upon how you're reading the question. And there's multiple questions that are being asked essentially with each point. And what I've done here is I've kind of tried to change the font on the wording that's going to differentiate each one of the 5. As an example, number 1 says provide an overview of the use of modern software engineering tools. So we got modern software engineering tools here, necessary for today's effective engineering practice. All right, so the focus is the overview of the software engineering tools. And then you're going to see like a series of questions on here. You don't have to answer, and I don't want you to answer all of the questions, like, question number 1. It's not question number 1, question number 2. That's the midterm. This is an essay that includes answers to these questions in terms of the way you're putting it together. So you want to provide a consistent, introduction, body paragraphs, conclusion, kind of format to it for which you have addressed the questions, and the questions in this particular case, how are modern day software engineering problems being solved, as an example. What tools, methodologies, exist, and what are their popular use today? How has this changed from recent years? What benefits do the new tools provide? And you're probably wondering, well, what new tools? Maybe, I don't know. So you might have to go online. You might have to actually do some research. The questions aren't going to be something where you can regurgitate out of a lecture or regurgitate out of a textbook. You actually have to go out and say, well, what kind of new tools are out there? What's going on? It's an opportunity for you to research, which is where those 3 references come into. Research what's going on in software engineering. What are some of the new techniques? Agile software as an example, agile development, and some of the other things that are going on, object-oriented approaches and stuff. And focus on, you can focus on one tool, you can focus on a lot of tools, you can do a whole survey. You can pretty much approach it any way you want. When you find information, I don't want you to cut and paste a URL from some company tool. It's not a book report where you find a tool out there and you're just telling me about that one tool and you provide a reference for it. I want you to actually kind of approach the topic as in the use of it for software engineering practices and more of a survey. Because what ends up happening is if you find a tool out there and you start cutting and pasting stuff off the website for that tool, your paper is going to come back plagiarized, essentially, because you're regurgitating information that's on the internet, which is not really the purpose of this. So when you go out and look for stuff, you can find journal articles, you can find trade references, you can find websites if you want, but make sure to properly reference them. So you have to have a reference page at the end. Now I say 3, you can have more than 3 sources. 3 sources is kind of small, actually, but might be enough for a 3-page paper, 3 to 5-page paper. So 3 would probably be accurate. It's not going to be overkill, it's not going to be underkill, but you're more than willing to have more. Which also means you're probably going to want to integrate the literature somehow. So as you're writing this particular paper, you can say, so-and-so from XYZ company said such and such, and then provide quotation marks when you're using somebody else's words. And at the end, last name, author's last name, comma, the year, or however you're referencing it. You can also paraphrase or summarize or do some other kind of ways of integrating the literature into your paper. If you don't want to do that, there's no requirement on the number of in-text reference citations, which is referred to as in-text because it's inside the body of the paper versus at the end. There's no quote on that either, but it's a great opportunity for you to practice kind of referencing things if you want to do it that way. But you must find 3 sources that are all different. And hopefully they're not all websites or something. I mean, if that's all you have access to, then I would actually try to look for a library that's on, like the ACM or IEEE or something, or some sort of a non-commercial source. I could be really strict and say peer-reviewed source or something, but I'm not going to go that far. If you just find 3 sources and use it, I think that's going to be appropriate. The second question. Okay, so the first question is all about practices, tools, modern day. So you could do a survey, you could focus on 1 or 2 if you wanted to. The second question is you're going to provide, if you pick this one, that is, we're asked to provide an overview of risk management and processes for software engineering projects. So describe a plan, and how you would carry it out, and provide examples or use a case study to demonstrate your points. So you could approach, let's say, number 2 in terms of risk management. In fact, you can use this approach with number 1 or some of the rest of them as well. Pick a company or pick a project and say, for this particular project at this company, and then briefly describe the company or the project. Say, this is the risk management plan I would propose to use. These are the processes I would go through to create this plan, and this is how I would assemble it. And these are some of the important phases in the plan and some of the important content that might exist. And you could use a case study, which means, let's say, for example, there was a company that had a failure, something went wrong. You could say, well, this is what happened, and this is how I would implement. If I were doing this, and we're just starting all this over again, and we were to fix this, then we would use this particular risk management plan, or something like that. If you do that, it's actually kind of easy, because then you could take the case study and reference it, and there's one of your references right there. And then you can do some research on risk management, perhaps, find a book on it, and then reference something out of that book, or use that book information or something. So you can kind of incorporate a lot of different techniques in that. The next one is on software testing. And so we can describe how, if you wanted to, describe how software testing can be performed. Provide an overview of the testing plan in detail, how each one of the processes be performed, conducted. Demonstrate your points with examples, a sample project or case study. Most of these questions are going to say demonstrate your point with examples, case study, or something of that nature. Only because it makes more sense to apply the concept to a real business environment, or to a case study, or to a problem set, or to a project. You can use one, you can use many. You can, in fact, if you don't like, say I don't want to use a case study approach to this, I want to, just give some examples about testing. You can say, well, for this type of testing, here's an example. For this type of testing, here's an example. For this way. So you have freedom to interpret the way you want to do something. I would recommend that you provide examples. Each one of the questions that really wants you to do it says it in the question. You can do, if you don't like examples, you can get away with just one small example, perhaps, in the entire paper, without using very much examples at all. And, the more examples you use, it's actually going to add volume to the paper, normally, because you have something to talk about and have something to relate the information to. And some people prefer to talk about examples because then it makes it sound more like realistic. I mean, it sounds more thought out when you can actually apply the concept to a real-world scenario. So, let's see, question number 4. Actually, there's 6 of them here. How'd that end up? I thought I had 5. Oh well, 6. That's okay. 6 is good too. You only pick one, so you don't have to worry how many there are. So, so the next one says, what's the difference between software reliability, dependability, and security? Ooh, so this one gets you to start thinking about some of the stuff we've been talking about in the last couple weeks, in terms of what's dependability, what's reliability, what's security, and how does that work, and how those concepts work together. And you're not going to find a paper already written on this anyway. But describing the concepts, explaining how they differ, providing examples, demonstrating each one of them, perhaps, developing projects, what are some of the things to look out for, key features of the project development, either in the product or in the project plan, the development plan, or methodology. And provide an overview to make clear distinctions between these two, between these different software qualities, in terms of what they mean in the development process. Number 5, we actually haven't talked about yet. It's coming up in the lectures. It's Agile software development. Taking a look at that as a concept. Providing a demonstration for a sample project. How would you apply that? We haven't talked about it yet, but this CSLO essay covers the entire course, and we're only at the midpoint. So you might wait if you wanted to do that one for the information I am going to provide, or you could probably get some better research as well online. Demonstrating projects, how the concepts are implemented. And then the last one, engineering, modern software engineering tools and development environments. So the first question was basically on use of software engineering tools. It was kind of generic. The last one's sort of similar to it, but this one is, you could gear this one towards more of the environment. So provide an overview comparing different, so this one says provide an overview comparing different environments, or compare 2 or more and focus on one of the particular ones that might provide a detailed overview of, let's say, a development environment, what it offers, how it can be used successfully for software development projects and stuff like that. So this is more on the environment. This one up here is more on the tools. It doesn't really matter what category your paper falls into. You're only writing one paper. You could focus more on number 1, or you could focus more on number 6 if you wanted to, if you're talking about tools and things of that nature. And you don't have to actually, when you write your paper and you turn it in, you don't have to tell me which one you've selected either, because I'm going to find out by reading it, hopefully, which one you've selected. So. And you have a little bit of academic freedom, I would say, in terms of the interpretation of it. If you want to go off on a tangent and talk about, say, for example, the development environment, if you wanted to talk about Visual Studio or something like that as a development tool for source code writing, you could talk about maybe source code maintenance or something, or version control or configuration management or something, if you wanted to talk about that, and not cover a lot of the other environment stuff. And you might not even do a comparison between one environment and another. It's basically the topic or the theme that I'm interested in having you write about. I don't want you to pick something that's not on here. You have to pick something that's one of the 6, essentially. Questions about the midterm? Excuse me, the CSLO. That's what I was talking about. Nobody even caught that. No? The CSLO essay is not due until the very, very last day of class. Remember that part. Midterm's not due for another month. It's due in a month, I should say. And I'm sure we'll have more questions as you guys start working on it. Both of the 2 assignments do get uploaded into the ITU EMS along with everything else. The links are not created yet. They'll be created next week. And I believe next week is when we're going to start thinking about the final exam schedule. And it may not be posted next week, but will be posted in the coming week probably. So about another 2 weeks, just in case you're thinking about making some plans for travel or something. You'll know exactly when you have to be here on what exact day. And then obviously there's some flexibility in terms of the scheduling. So you can sort of figure out how to work things out. This one is lecture 8. So, yes? I'm sorry, one more time, I didn't hear you. Go over assignment 3? Seriously? I have to go get it. Did we go over assignment 3 yet? I'm sorry? Yes, we can. Please go over assignment 3. Yes. Let me locate assignment 3 real quick here. I don't want to. No, hold on. It's a couple clicks away. I'll find it. Assignment number 3. I forgot. You're the one who's finishing the class like now. For those of you who are working ahead and are interested in assignment number 3, and while this is loading, another administrative thing, we have a roster going around that you need to sign. Make sure you get credit for being here. Okay, so assignment number 3 deals with the concept of feasibility studies. And we actually haven't really talked about feasibility. Actually, that's coming up. After testing, I talk about forecasting, feasibility, planning, estimating, costing out software to see how much labor is going to be involved, how much it's going to cost. We can allocate resources correctly, and budgeting, things of that nature, which is coming up next. But let's talk about feasibility for a second. We have a little scenario that's being described, and the scenario gets into the responsibilities, the description of the project, and then we have the end of the scenario. I'm not going to read through the scenario, but know that you're going to have to read through and kind of read through it a couple of times, make some notes as you're reading through it, so you can kind of get a feel for what the project is all about. At the end of the scenario, you have to answer the following questions. And the following questions are based upon some feasibility lecture material that I'm going to cover in the coming weeks. So if you're thinking about doing this now, just look ahead actually in the schedule set and you'll see the lectures for that. So based on the given scenario that is above, what kinds of questions would you ask to assess the initial feasibility of the project information? And does the project seem feasible? Well, I can tell you right now, in fact, you probably already know what feasibility means in terms of software engineering. But to kind of give you a little background on that to start out with, because you're going to need that in order to actually understand the question. Usually people consider feasibility right in the beginning, right before requirements actually get created. And a feasibility study is the go or no-go decision, which says we're going to be able to make this, or we don't want to make this at all. We'd rather walk away from this. And feasibility can be based upon technical limitations, financial limitations, resources, equipment, time, people, and then also the overall concept. And the concept might be something that's too new, too old, A feasibility may also refer to whether or not there's a perceivable profit in the end or perceivable acceptance. If, for example, you don't see a way of satisfying the customer's requirements because the customer has, for example, contradicted themselves back and forth, it may not be feasible to deliver a solution to this problem to them. So when you read through, that's why I said probably going to read through it a couple of times and make some notes as you're reading through it. And if you read the questions first, then you'll have some ideas about what to jot down. One of the important things is to keep in mind and ask, what kinds of questions, for example, for this first one, what kinds of questions would you ask the client, the people that you would be building this for, to assess the initial feasibility of the project information. So it might be, when do you want this? How much are you willing to spend on this? So time, cost questions might be associated with that. Also technical questions. Let's say, for example, they're talking about a new TV remote control, but they're talking about doing it from, 10,000 yards away or something. Obviously you're not going to get lines of sight correctly. So questions about the features of the product might be something that might also apply. If you go back up and you read through the description, you're going to see it's a system that needs to be developed. If I remember this right, I think it's for a healthcare program, a healthcare medical facility. Looks like we're combining people from a clinic. So the scenario is pretty much going to give away some hints in terms of, after you read the scenario, you might actually have some questions you might be thinking about in terms of, understanding the requirements or understanding the product. Because another part of feasibility is whether or not the development team actually understands what they're building and whether or not they're even capable of understanding. Some technologies are very specific towards different fields for which you might not necessarily have a background for. You might be building a heart monitor. I keep using that example, but it's kind of a generic example, I guess. But I guess you'd have to know something about medical practice. How the heart monitor is installed, maybe, I don't know. Maybe what it does, how it works, which the development team may not necessarily have knowledge of that either. So you could probably take feasibility out and think of it in terms of a lot of different angles. It means a lot. It's like saying engineer. It's a generic word. The second one here, describe what will the plan of action in the Century Health Century Health Clinic Management decide if they decide to contract your services to perform their preliminary investigation. What will be the plan of action? The plan of action is going to be specific towards that problem description, and you're not going to get that information until you read that problem description. Same thing with the feasibility. So you can't take this. There's no textbook that's going to give you a generic plan of action on anything, seriously, because it doesn't exist. Every project is different when it comes to feasibility. They have different factors to consider. Every project is different in terms of the plan to even conduct the feasibility study or the preliminary investigation that might exist. And I'm sorry? About skin analysis? A risk analysis? No, actually the question and what I'm trying to get at here is you're describing the plan of action. If you are going to take this contract for the service of creating this project or performing the project, what would your plan be? Think of it sort of like, if you were doing this, what would you do? What would the first step, what would the second step, what would the third step be? How would you actually go about conducting this? How would you perform your preliminary investigation? You might want to do interviews, you might want to go out and see what's available, you might consult with an expert, you might have a focus group, you might brainstorm, you have to actually kind of think about it a little bit, come up with some creative ideas. If you were doing this, how would you do it? What would your plan of attack be in terms of it? In fact, that's kind of the same as number one. What questions are you going to ask? How are you going to assess whether or not the project's even feasible? And then the last question is, what type of information is needed when you begin the preliminary investigation? And from whom will you obtain it from? Are you going to get from a third-party source? Are you going to rely upon what these people are telling you? Are you going to verify the information? And what techniques will you use in your fact-finding? You don't want to base everything off of the internet, obviously. You're probably going to look at some technical reports, some specifications, some manuals, and or perhaps, I don't know, findings from other research that you might be doing in terms of the requirements. So, you know, the way that you answer this is going to be your interpretation of what the problems might be and your approach. And this is an exercise in going through the feasibility section, finding out, you know, how difficult it is to actually put a yes, we're going to do it, no, we're not going to do it. Because you can't base it, the point being you can't base it off of one thing. If someone says, here, I'll give you $1 million if you build this project, half of you probably, okay, I'll take it. But when you look at the numbers, that $1 million might not be enough. You might spend more than $1 million putting this project together. In that case, you probably should say no. But, you know, until you think about it, until you learn how to assess it, and this is really just analytical skills, just until you've actually kind of gone through the thought process, it might not be feasible, it might not be possible. And then what are you going to do, take the money and then not deliver? Yeah, that's what most people would do, probably. Okay, here, I'll take your money, and then you go. That's why most customers are going to tell you you need to produce something before you get part of your money. All right, so what are you doing fundamentally when you turn this assignment in? You're submitting your assignment in the form of a written paper, approximately 2 to 4 pages, double-spaced in length, where you can format it any way you want. If you want to write a written paper that has question number 1, question number 2, question number 3, you can answer the questions like that. If not, you can write a formal, like, reports and put it together with an introduction and conclusion and some body paragraphs and say, for this particular company, we have these feasibility questions to ask, and this is the plan of action, and this is the type of information that we're going to put together, and mix it all together if you want, write it all together in one paper. Which, personally, I think I would do, instead of going 1, 2, 3. But it's your choice. If you don't want to organize it that way, you can answer the questions. When I say I don't require any references or anything like that for this particular assignment. This particular assignment is kind of left open to interpretation as well. Any questions about assignment number 3? Should we go on to 4 and 5 while we're here? Has anyone started number 2 yet? I know most students wait, but we are at the midterm. In fact, I believe that we have, let's take a little visit here while I'm on a tangent. We have, oops, where'd that link go? I closed it. All right, let's wait for it to come up. Oh, incidentally, if you have experienced any problems with the bhacker.com website, well, now it has an internet problem, but the problems have been corrected. I had a little problem earlier in the week with the database. And I think the database, the fans on the server, the computer that was running the database was full with dirt and dust. So I had to take the cover off of it, blow the fans out. The thing was overheating. So it was definitely, I wouldn't say technology challenged, it was dirt challenged earlier this week. But it is up and running, and it is running phenomenally good recently. Since probably because I upgraded the RAM on it too. So it's taking well, now this is really bad because when I click on it, nothing happens, but it has been very responsive lately. There are 5 assignments. I would say you should probably be finishing number 2. Next week is when I was actually going to do number 3, but I've done it already, so I don't have to. And then we have 4 and 5. Does anybody want to preview on those, or do we want to move on to defect testing? Move on? Okay, good. Let's move on. Your choice. Buyer, what do they call it? Customer's always right, or something like that? I don't know. I was going to say buyer beware. Buyer beware. Student beware. All right, this is like 60-something slides, but you know what? I'm not going to spend that much time on it. What I want to do is kind of highlight a few things, because this reads like a textbook. And if you've taken a testing class, this is a total repeat of everything you've ever heard of. But I want to apply it to software engineering because the last time I talked about testing in terms of the test plan, This time I want to highlight a few of the technical details of the test plan and put it all together. This is our last lecture on testing. Next week we move on to different topics. So this particular one focuses on defect testing as well as other types of testing tools, and it kind of loads you with some ideas about what to further research in terms of knowledgeable testing background for either the midterm or also for any particular project that you might be working on. So testing programs to establish the presence of system defects is what we're looking at. And we do testing to find defects, by the way. We don't normally do testing for reliability, for dependability, or for anything else. We do testing to find defects in software. Reliability is a side effect sometimes, or dependability could also be considered a side effect, meaning that if we haven't tested and we haven't found the defects, we're not going to have a high reliability or dependability score. So it all does work together, but traditionally what we're looking at is finding defects or faults. Not necessarily, I shouldn't go back to say this again, I said the word faults. Not necessarily faults, because we could have a defect that doesn't create a fault. Do you want me to move that? You can move it over. Is it in your way? Oh. Are you trying to copy something from earlier today? We can move it over if it's blocking the screen. For those people sitting over there, it probably is blocking. In fact, I'm probably blocking the screen for those people sitting over there. Alright, so what we're going to do is understand the testing techniques geared towards discovering program faults. And just because we have a fault doesn't necessarily mean we haven't done our testing, because we know software is not 100% reliable. And we're going to introduce some guidelines for interface testing and look at some approaches for object-oriented testing. And understand principles of case tools for support for testing as well. So I'm going to highlight a couple of objects. This is not a replacement for an entire course in testing. That's actually a good idea. If you're especially going to be working, hopefully, most of your career in software engineering, it's not a bad idea to take a testing tools course, because then you'll see the hands-on techniques that are being used and the software that's available to automate some of the stuff. So we're going to cover defects, integration, object-oriented, test benchmarking. Test benches, excuse me. So the testing process we looked at last week, actually. I believe we did testing last week, right? Somebody remind me. Yes? Okay. Yes, okay, good. I'm sorry? Oh, we didn't finish it? Security? I didn't finish that lecture? Hey, remind me next time. I'll go back and do it. Next week we'll finish that lecture, because I'm already on this one. I don't want to stop again. So, actually, I could probably cover it. No, there's no overlap. Remind me. See, my TA is supposed to remind me, TA, that I didn't finish last week's lecture. Oh well, I'm gonna blame it on you. I'm sorry? You weren't here last time. That's why you didn't remind me. Good answer. All right. So next week, as I'm reminded, I didn't finish last week's lecture. So next week I'll finish last week's lecture. No biggie. It's on a totally different topic. Looked at security and authentication and stuff like that, which is actually not bad. But let's get through this. All right. So we have component and integration testing. This I did cover last week, I believe. The different testing types. An overview of the particular types that are mixed together in terms of a testing plan, because we don't want to do just one type of testing. And also important to note is that these particular types and processes happen throughout the development lifecycle, not just at the end. And the different types can be mixed in at different phases depending upon what information and data is available, because I want to talk about the concept of test data and the use of that data. So in terms of the component testing, what we're looking at is the individual program components. In terms of the integration, we're looking at putting the components together, and we're having them work together and to integrate the system. In terms of the testing phases, this picture kind of summarizes everything that was in that previous slide. So we've got the component testing from the software developer's perspective that goes into the integration testing, which is an independent testing team, hopefully. So parts of the issues associated with testing is who does it. So certain things can be done by developers, certain things should not be done by developers. They're not always the best eyes for finding bugs or for even analyzing and looking and running the test, because they'll do something completely different than an end user will or a different team. So it's not a bad idea to have multiple teams. In terms of the defect testing, the goal is to discover defects. A successful defect test is a test which causes the program to behave in some sort of a wrong way, so in an anonymously way as well, with different types of data. So what you end up having is the situation where it doesn't really matter which type of data you give it, it's going to come out with hopefully the correct answer, or it's going to hopefully not have a defect. Because what we're trying to do is test in a non-working environment. Because everyone knows the testing environment is not really the real environment. Until the end user who's installed it on their computer calls you up and tells you there's a problem, you don't know how it's really running in a true environment. Which is one of the issues associated with testing. And it shows the presence, not the absence of a defect. So we can't tell if it's not there. We can only tell if it's there in terms of the theory. In terms of the priorities, it's not always the biggest features. It's not always we actually have to plan out and put a priority on it. So only exhaustive testing can show a program free of defects. Exhaustive testing is impossible. We can't test everything. And that actually brings up the coverage concept. What we can not test it exhaustively every component with 100% full coverage. What we do is we pick pieces and we hopefully cover the entire program and all the major functionality, and we hopefully hit the important aspects of it, hopefully. However, that focus is wrong as well, because what we perceive as being important may not necessarily be associated with any particular defects that might exist. And so some unimportant feature that we've put in, something that we think is a very low priority in terms of the functionality, might be causing the biggest bugs of the system, might be causing the biggest defects. And you'd hate a small little thing like that, like a missing input screen, or a control that doesn't work. You know, you have a fancy printing device, but the print option is grayed out when you're supposed to use it. It could basically render the entire feature unusable, and you might not consider that as an important feature or a high priority feature. So tests should be exercised at the system capabilities rather than at the component level. In terms of the exhaustive testing, each component you can test it and test it and test it, but the integration is probably more important as a higher priority. Testing old capabilities is more important than testing new capabilities, because once you add something new to the system, as we've seen last week in the discussion, that it can have a dominoes effect, which is why regression testing is important in going back through and making sure you can verify that what you've previously tested still works, it hasn't been broken. And then testing typical situations is more important than boundary value cases. Like, typically, what would a user put in for a password? Instead of how long the password can be, or how short you can make the password. Because what we're trying to do is mimic and predict ahead of time what the user is going to do without the user doing it, which makes it interesting. We've all heard of the concept of test data and test cases. We get this. We've got this in Software Engineering 1. We created test cases, whether they're use cases, scenario-based cases, or whether or not they're electronic, automated test cases. We put that together and then we use test data. The selection of both is very important, actually. The data, it's the inputs which have been devised to test the system. The cases are the inputs to test the system and predict the outputs from those particular systems in terms of, you know, this is what we're expecting, this is what we got, it passed or it failed in terms of the case. And here's how the two of them work together. In terms of defect testing, they design the test case, run the test case, prepare some test data for it, and we have the test data. And this is basically the data, the case, the data, the results, and the reports that come out of it. This is the process that we're going through in terms of the development of the kit, running it, development of it, running of it, comparing the results, and working with it from and although it kind of looks like two separate kind of components that are working together, it really is actually. You've got the design of the test case, then you've got the running of the test. You've got the data and the output from the data, as well as the results to consider. So we looked at this last week. In fact, I think I called it open box, closed box, maybe, or last box, green box, red box, blue box, black box, white box. Another example of it being the outside, you can't see inside, it's dark. versus the white, where you can actually see inside of it, and you can actually kind of test the code itself. And the reason why this is in here is because I want to give you some examples of some common approaches that you would add to the test plan so that you could actually accomplish black box when you're intending to accomplish black box, and vice versa with the white. So when, just to refresh your memory on the black box, it's based on the system specification. What is the system supposed to do? And it's usually based on the requirement specification. So black box is really requirements analysis, making sure we have got all of the features implemented. And here we have the inputs causing the anonymous behavior, and in terms of our test input data, it gets into the system, and then we have the output. So really with black box, we're testing inputs, processing, and output. But we're not really focusing on the processing part of it. Instead, we're just looking and comparing the inputs with the outputs and reviewing whether or not we got the expected results, which gives us the behavior that we're looking for. And then we have this concept called equivalence partitioning. So the input data and the output result often fall into different classes where all of the members of the class are related. So we have different classes. Each of these classes is an equivalent partition where the program behaves in an equivalent way for each one of the class members. So you think of them as categories. We have good data, we have bad data, invalid, valid. We have data to test this, data to test that. We put them in different classes or categories, and there is a direct correlation between the input and the output in terms of the results and expected output that should be occurring. Test cases should be chosen for each one of the partitions, which means we're taking the system and we're saying, well, let's test this, let's test that. We partition it out, and we have equivalence, a bunch of equivalence tests instead of just one as a concept. So you could essentially take, and here's our example here where we've got invalid, valid going into a system. We have outputs that are testing, and they consider it equivalence because we're taking a grouping. They're all equivalent. These are all equivalent bad ones. These are all equivalent good ones. And we're running it through the system and saying, well, equivalently, all this group should give us this set of results as an output. That group should give us that set of results. And if we've partitioned it correctly, then we can kind of evenly distribute all of the functionality over the tests using the appropriate test data, and kind of come out with some sort of consensus as to which features might be causing a problem if there is a case in which a defect exists. So it's just terminology put on there. The partition the system and the inputs and the outputs into equivalent sets. Here's an example. So if an input is a 5-digit integer between 10,000 and 99,999, equivalent partitions are going to be less than 10,000, or a range over the 10,000, above 10,000. Between this and this kind of thing. So you choose test cases at the boundaries of each one of the tests, hopefully. So it's just a way of kind of figuring out the data that you're going to use and the span. It's not really coverage, it's more equivalence, because you're taking a grouping. These are all equivalent, those are all equivalent. Because it's not very effective. Let's say you have 10,000 data points to work with. You're not going to test all 10,000. Instead, you're going to test one in this range, one in this range, one in this range. And then that test result comes back is going to be equivalent to everything else in that particular range. So you can basically save time and energy, not have to test every single input, every single output. Because a common mistake actually is people get too exhaustive. They have all these test cases to test practically every input possible when it's redundant and it's unnecessary. That test you just ran is equivalent to that one over there, to that one over there. So if you build equivalence into the scheme, into the design, it cuts down on the amount of work, it creates more reliable results with a more predictable kind of coverage. So in terms of our partitions, less than 4, between 4 and 10, more than 10. And it's interesting because depending upon how you're designing this and you're running your test data through, you might actually have a defect but never find it. Because it might be on the border of the range. It might be slightly under the range. It might be over the range. It might not fit into the range. You may not have tested all the ranges. You may have left out a grouping or something. You may have said less than 4 and then between 5 and 10. So you didn't test 4 or something. which is actually kind of common because all the stuff can come back and come back error-free. And all your tests can pass, essentially. But you still have a defect, which makes the test, not really that efficient. So search routine specifications in terms of precondition, postconditions, or any other type of condition that might exist, depending upon the logic. You can also test those with equivalent ranges. And what we're looking at here is we have input partitions. We're taking the partitions and just think about flow control in a program. If something's less than a certain value, it gets routed this way. More gets routed this way. So you can basically design the testing to go along those paths to test the routes. So the inputs which conform to preconditions, inputs where the precondition does not hold, maybe as an example. Inputs where the key element is a member of the array, or the inputs where the key element is not a member of a particular array. You exceeded the bounds of an array, you've gone too short. Perhaps at the end there's an empty array, null value or something like that in there. And that pretty much helps you kind of design tests that's going to cover everything in terms of all the possible inputs. And then sequences in terms of guidelines. And some of you are probably looking at this going, well, that sounds like what programmers do. It is. From a white box perspective, when you are writing the code, most people would actually kind of go through the scenarios and say, okay, it's going this way. Okay, it's going this way. This case is going to be used. This if, then, else. And some people actually put in things that get printed to the screen and say, okay, it made it here, made it here, made it here. And then you fix it. From a white box perspective, you might go through and find a problem. And then you correct the problem. This approach actually kind of takes it from an external view instead of the internal view. Still from a white or black box kind of approach, but mostly a black in which we don't know. And we're testing it because that particular loop was mixed in with other loops, with other flow control patterns. And that's why I say the integration of everything put together is probably the most important thing to test, because it doesn't really matter if the condition works okay with the if-else. If you have an else on the bottom, everything just went through everything, and just bypassed all the logic or something. Or maybe the value was just too small to begin with or something. Okay, for sequences, so for test guidelines. So testing software with sequences, which have only a single value. So using sequences of different sizes for different tests themselves, and then drive tests so that the first, middle, and the last element of the sequence are accessed and used or tested. And then test with sequences of zero length in terms of what's happening in terms of the flow of that. And here's some input partitions that you can design for sequences in which you have an array, array elements. And on the top here we have single value. Is it in the sequence? Is it not in the sequence? More than one value, first element, last element, middle elements. And then looking at in terms of the input sequence from a key to an output. And basically trying to analyze manually from all of the different logic that might appear so you can accommodate for examples for input data that was going to test each one of the different logical points or decisions that might be making throughout. So structural testing, another very popular kind of an approach, sometimes called white box testing. And I think we said open box last time, closed box, open box. I don't know. Anything essentially is not standard when it comes to this. So the terminology, white box and black box are probably the most popular. So. Okay, so what we're looking at is the inside of the box. We're looking at the code itself. And derivatives of the test according to the program structure, knowledge of the program is used. And usually programmers would do this, would actually perform it. However, it's probably even more beneficial to have somebody else do it rather than the person who wrote the code. And the objective is to exercise all of the program statements, and not all the path combinations, but the program statements. Make sure the paths are correct. So here's an example where we've taken some test data, and we've put it into some component code, which drives the test data, and then that pretty much goes into the test outputs that come out of it. So we're testing to see if every path through the program is accessible. We are testing to see if the particular loop actually goes the number of times it's supposed to. The particular function actually gets called correctly and has the correct return value. It's in the correct format. So it's really an internal kind of process. And if you've never seen source code before, here you go. This is a binary search source code written in Java. It's too small, you can't read it, and I'm not even going to talk about it. But what we're doing, and the reason why this slide is here, is showing you, this is what we're testing. We're testing the source code. And in terms of the binary search example of this, just imagine any binary search you've ever written in Java. We can look at equivalent partitions. We look at the same concept. We want to partition out we want equivalence testing. We're going to partition out the inputs into different categories. We're going to try and basically take the same similar approach but apply it to a white box instead of a black box. So what we're looking at as an example of this list here, preconditions satisfied. The key element in the array is the precondition. If it's satisfied, is the key element not in the array. And what we're looking at is dividing out and kind of going through the logic of performing a binary search and looking at, and I'm going to assume you guys all know what a binary search is, hopefully. If not, you're taking a whole group of stuff. Hopefully it's ordered. If it's not ordered, you got to put it in order. Cut it in half. Say, is the value I'm looking for on this side or this side? Oh, it's on this side. Okay, good. Throw away the rest of it. Now I got this side. Cut that in half. Is it on this side or this side? Cut that in half. This side or this side? And basically you find the number you're looking for, or you find the information by process of elimination. Because after you've thrown away all the not equal to's, you're going to find the one it's actually equal to. And in terms of testing that kind of logic, you would have to run through in this particular slide showing you some examples of how the input would be compared. Is it the key value? Because sometimes when you look at the first item and it's found right there. If not, then you cut it in half and you look for it. So, all right, here's the equivalence partition. So we have the equivalence class boundaries. Element is less than the middle. Element is larger than the middle. We can find the midpoint, cut it in half, and eliminate the half in which the item may not be found in. So it's like people going, I'm thinking of a number between 1 and 50. And they go, 25. Is it higher or lower? Lower. So now I can get rid of 25 and above and only search through. Now you can guess between 1 and 25 now. So, which is essentially what that search is doing in another example. Oops, let's see. Some test cases that might come out of it in terms of the input and the equivalence inputs. So, because what you don't want to do is go through 1 through 25. You'd rather pick something in the middle, maybe. It's like how most people would logically actually guess at something. So, unless you think, a number is a certain way, then you're going to say 19, 18, 17, 16, which is not a good, effective guessing method. So, okay, so path testing. So this is basically looking at the logic, breaking out the test groups, creating test cases to accommodate for the input values that might be in a particular range that might satisfy the equivalence for each one of the partitions that might be created in that. Path testing, this is where you go through the if, else, then, none of the above, default, go through this case statement, to make sure you can actually get to where it is you're supposed to be going through in terms of the path. The objective of path testing is to ensure that the set of test cases in such that each path through the program is executed at least once. Because what you don't want to do, and this is what a lot of programmers actually do, they use the same piece of test data. You put the test data in, and it always takes you to the same path. So you're always taking the same route. It's almost like if you were testing the street clearance for the truck through a city, and you always took the truck down the same route, and it works. There may have been a side street it didn't go down that's too small for the truck, that it might actually not make it through, which could cause a problem. But you never went down that street, which means your program's going to have full defect-free status, but lo and behold, someone's going to take the route, and the route's not going to be correct. This actually happens a lot too, because this is when you have really strange behavior that occurs. If you've ever worked into a support department, you hear the calls. Yeah, I get this really weird message that shows up on the screen. It says, call Mark, he's at lunch. Like, what does that mean? Because usually programmers actually like to put like really weird, well, in the old days, when you can get away with it, you can put like little messages in there, just in case the program really failed. It says, I am really failed, I really failed, reboot me now, or something, or call Mark, he's at lunch, or something, meaning, you know, oh, it went down something he was supposed to fix, but he hasn't fixed yet, you know, or something that says, you know, it made it this far. It's usually a debug message or something that somebody left in there that some customer was able to get at because their input brought them down a route that wasn't really even tested, that nobody even knew that message was left in there. A lot of error messages that come out of programs are coming out because we didn't test the path, actually, because if anyone had looked at that, they would have removed the message, essentially. Because you don't know anything about Mark being at lunch or something like that in a commercial software package that you're displaying out there. Or in Microsoft's case, a fatal error, fatal memory error, and a blue screen, which not necessarily desirable. So they got rid of that. So starting point for the path is the program flow chart. So you flow out the program in terms of make a tree out of it, and you traverse the tree, find all the paths. So the statements with the conditions are therefore nodes in the flow chart. I think I've got a tree coming up. Here's the tree. I'll go back and I'll explain the tree. But this is what it looks like. You go from 1 to 2 to 3 to 4, and you traverse through, and it shows you every single route through the program. And so you can design your test cases so that you're actually testing input that's going to take you to each one of the outputs that's going to be at the bottom of that route. And in terms of what we're looking at is we can use this. In fact, this came out originally as a metric to be used, and you can use this as a metric when in assignment number 2, actually, if you wanted to test the complexity of how hard it's going to be to test it. So, in fact, there's automated software tools that will build a tree out of your program and tell you how difficult it is. Because depending upon the length of the path, how many paths there are, how many different ways there's to get, it could be more or less effort to test it because you have to create so many test cases for each one of the paths. So these tools can actually tell you how difficult the program is going to be to test, which is how it originally came out, but you can design the test cases from it as well. So describe the program flow. Each branch is shown in a separate path, and you look through arrows so you can count the edges. So the complexity of it is the number of edges minus the number of nodes close to this particular example. And there's actually a couple of different schools of thought on how to build the trees and how to traverse the trees to count the nodes to actually figure out the complexity of the particular algorithm or particular program that you're testing. So you have the number of tests to test all of the control statements is equal to this particular number that you're getting out of it. That's a nice cell phone ring. And equals the number of conditions in the program, hopefully. And it's useful if used with care. Does not apply adequately of test. Well, actually, it's not a thorough testing mechanism either. In fact, if this is built incorrectly, your tests are all garbage. It doesn't really mean anything anyway, because you're not really testing anything if it's incorrect to start with. So here we have our binary search flow graph. This is what would happen essentially with that particular source code example. If we were to make a graph out of it, we have, is the bottom larger than the top? If we're cutting it in half, while the bottom is smaller than or equal to the top, we're going to perform something here. And essentially what we're doing is we're going through the logic of the program. People do this with the actual source code, or you could do it with the actual logic, which might not exactly match the design of the source code. In fact, I can kind of see where it would be better not to match the source code, because the programmer is going to do that, hopefully. Hopefully the programmer is going to actually test the loop, test the if-then-else structure, all of the constructs within that they're creating to make sure that they're actually legally written and that no errors are being produced and that the paths are working correctly. But it's nice to actually kind of apply this to a black box approach. Take the entire program, path it out in an arbitrary manner in which you're testing each one of the paths, but you're not necessarily specifying the path. And you're doing it from external. Then you can tell what happens and say, well, if the user saves the document twice, then it won't print, you know, because it just stops. It just nothing happens or something. Or if the user selects to open the file and the file is already open, it opens it twice instead of just telling the user that it's already open or something, which is functionality you're going to get from the external view, from a black box perspective. It's going to be testing the functionality in terms of its paths through the program and not necessarily the way the program was written. So, because the programmer is already going to hopefully test that. Nobody ever tests the external logic, usually. Independent paths, and we have, okay, number of the paths in this particular case, 1, 2, 3, 8, 9, takes us down this way in that first example. And we put the paths together, we list out all of the paths, that gives us our score on how difficult that is to test. But most importantly, we need to figure out what to test. So test cases should be derived so that all of the paths are executed, so you have at least one for each one of the sets, or each one of the combinations that occurs. Dynamic program analyzers may be used to check all the paths, make sure they've all been executed. In fact, this is where automated testing comes into handy in terms of the white box variety. There's a lot of it out there for C and C++. Java's got JUnit, but that's not really this type of testing. That's unit, that's class testing, which I'm going to get to in a few minutes for an object-oriented environment. And everything I've been looking at, everything I've been showing you so far is not object-oriented. It's all procedural style, old-style testing, is what I call it that. The integration testing is also another kind of an approach to it, where you test a complete system and as the subsystems are put together. And it's nice to do the integration testing as each subsystem is added to the system. That way you can actually tell which system caused the fluctuation or which caused the abnormalities to occur. And integration testing should be black box testing with tests derived from the specifications. So we're looking again at black box. In fact, believe it or not, if you think about it, you think, well, black box is so easy. That's one of the most under-tested areas. Everyone does white box. Nobody does any black box testing, which is kind of odd. I mean, they don't do as much as they should. The difficulty is localizing the errors, figuring out where the errors have come from, and not always blaming it on an internet connection or a network connection. Incremental integration testing reduces this problem, as I mentioned before. If you incrementally add a unit by unit, continuously test your increments, then you end up with a better result, a better way of actually predicting it. And here we have a test sequence 1, 2, and 3 where we've incrementally added more to it, and we're testing the integration of all of the units as they're put together. So approaches to integration testing, we got top down, bottom up. In fact, I covered this in Software Engineering 1, so I'll kind of skip over it a little bit. It depends on where you're going to start. You're going to start with the modules, or then work to the big unit, or you're going to start with the big unit, break it down into its modules, into its smaller points. Here's a little picture that kind of gives you the perspective on it. We have level 1, level 2, level 3. In terms of the different levels, if you're going to start at the top, you're going to start level 1 and break it down this way. And I think the next time is the opposite way. So if you're going to do bottom, you're going to start at the bottom and work your way up. And take the small pieces and put them together. This allows you to put dummy units in. This allows you to test units before the dummies and before the rest of the program is actually created. So you're going to take one of the two approaches depending upon what the objective is and how far along you are. If you are already done with most of the program, then that makes more sense, because you can kind of put it together in a hierarchy and go through each one of the flows. If you're testing it as you're developing it and you have nothing really much done, then you're starting at the lower levels and you're working your way up to the big picture, usually. In terms of the testing approaches, we have architectural validation. We have the system demonstration. This all leads into the final product that you're actually delivering in terms of your acceptance. The test implementation and the test observation. So in terms of the architectural validation, you're looking at a top-down integration. Better for discovering errors with the system architecture, meaning that it's an operating system issue, it's a network system issue or something, because you're looking at the top main running of the application, which isn't going to run if you've got a network problem. You're not going to discover that problem if you start from the bottom and work your way up, because the individual pieces are actually going to work just fine for you. The system demonstration of a top-down integration test allows you to limit the demonstration. So you've got, at earlier stages of the development, you may not have a module ready. You might put what I call a dummy module in there. Most people would demonstrate the system from top down. Look, here's the program. You go into this feature, you go into this feature, you go into that feature. In terms of the test implementation, often easier to go bottom up for integration testing, because what you're doing is you're trying to hopefully break out the abstraction and say, we're testing the print features, we're testing the email capabilities, we're testing the scanner interface, or whatever happens to be the lower level feature, and then work your way up. In terms of the observation problems with both approaches, extra code may be required to observe tests, actually, if you're going to observe it. Because you actually have to have a user account to test the entire system, let's say if it relies upon a user account. So. In terms of the interface testing, takes place when the modules or the subfaces are integrated into create the larger system. And this would be the interface with how this component connects with this component here. And we think more of interfaces when we think about classes. And it has the public interface. Is it compatible with the driver, and is the driver actually expecting this public interface? And then, are the classes communicating? Are they speaking the same language back and forth? So the objects are, the objectives are to defect faults due to the interface errors, wrong number of parameters, wrong message, typos, or something of that nature. And then it's important for object-oriented development and objects as they are defined by their interfaces. So if we already have a pre-existing library, are we calling the right methods on the objects? Are we giving it the right set of parameters? Which could cause a serious problem, actually, especially if the library changes, which is actually kind of common. Somebody makes a slight change, they capitalize the first character of something, or they lowercase it, or something happens in which the interface has changed slightly, and then nobody figures out that the interface has changed until the program's broken and they have a defect somehow. In terms of the interface testing, we have test cases here that work to say that A can talk to B, that can talk to C, and everybody's communicating, sending messages back and forth. And true for object orientation, also true for non-object orientation applications. I don't want to give you the impression that interface testing is only used for object orientation. It's actually used for traditional style structural code, procedural code as well. Interface types, parameter interfaces, I mentioned before in my example, the right number of parameters, the right data types, the right order. Shared memory interfaces, are they both going at the same database location, the same memory that's in some sort of a procedure that's stored in a dynamic memory allocation kind of thing. Procedural interfaces, is the function, does a procedure function module exist? Does the interface actually get called correctly? Message passing, that's one method calling another on another object, or invoking a method on an object to make sure that the message actually gets passed back and forth between the objects correctly. And then we have interface errors. We have interface misuse, using the wrong interface. Or we have programs that make everything public when it really should be private or something, and they make a public interface to something that ruins the integrity of the object because somebody uses it when they shouldn't use it. And you called the wrong, let's say called the wrong method on something, or used something incorrectly. Interface misunderstandings. Oh, I thought we were supposed to do it this way. So we're calling a driver to do something, and we're asking the driver, oh, it's not this driver, it's the other driver. We're calling the wrong driver, or we're calling the wrong module for something. Although it works for some things, but it's a beta model. It's half implemented and it's missing the rest of the functionality or something. Timing errors, calling one before the other, not calling one at all. Calling components operate at different speeds. So you might have something that is waiting for a response but then doesn't wait for it. Just continues working without the response. You get that with database connectivity and network errors, essentially. Timing between connections. Interface testing guidelines. So we can design tests so the parameter to a call procedures are the extreme ends of the ranges. So put the biggest number possible in there, or the smallest number, or put negative numbers in there if you're testing a parameter. Always test the pointer parameters and null pointers if you're working with a pointer environment, which is kind of antique these days. Pointers are kind of a thing of the past, sort of, Java and stuff like that. Design tests which cause the component to fail. So we're looking for a failure specifically. Use stress testing in message passing systems and in shared memory systems. Vary the order where the components are actually activated. That's actually kind of interesting. Most people will follow the same order, the same test pattern. Okay. Call this server, call that server, but reverse the order around. Sometimes you need a piece of information that you don't have that to get to A, B, or C that maybe have been accumulated or cached in previous steps that may not exist if you switch the order of the steps, because not every user is going to follow the same sets, or every interface is going to actually follow through the same steps. In terms of stress testing, you're exercising the system beyond its maximum design load. You're filling up the database with thousands and millions of records, which, believe it or not, a lot of people don't do. You know, they produce a system, and then the customer loads it up with data, and then they go, how come it doesn't run? Well, we tested it with 10 database records in there, and you have 10,000 or something. You have something a little bit higher than that. So stressing the system causes the defects to come to light normally. Failures, memory problems, failures, incompatibilities. And testing the system, test failure behavior. What happens when the system actually fails? Do we get the blue screen that comes out? Or do we out of memory errors and stuff? And then stress testing checks for unacceptable loss of service or data as well. How long does it take for the system to respond to the error message? Which is kind of interesting, because programmers put error messages in there, but does the error message actually work? And is it sitting behind another screen that we can't see, and the other screen's locked, which happens all the time actually. But it's there, and the user just waits forever until they reboot the system or something. So it might be unacceptable, actually. The behavior of the error messages might be unacceptable in the way that they're used. Particular relevance to distributed systems, which can exhibit severe degradation as the network becomes overloaded as well. Yeah, you can have, even connections to databases can cause problems, actually. In fact, I saw it with my bhacker.com website. My database server was going through a meltdown, and the interface to it, that PHP BB actually kind of connects to the database every time it does anything. So it was failing intermittently when really it was just the database that I needed to take the cover off and blow the dust off of it so it would stop overheating and rebooting itself. So small little technical problems. Object-oriented testing, we are getting to the end of this, don't worry. In terms of that, the testing environment is pretty much the same. However, we're testing different components, and there's a different style of testing. And there are object-oriented test suites out there and testing methodologies that are used. And it's not just language-based. It's not like you can't just get JUnit and say you're done testing. That's not really going to work for you. So the components to be tested are the object classes and the instantiations of the objects. So we have to have a testing environment that's actually creating objects for us, which makes object-oriented testing kind of a challenge for non-technical people. For testing engineers, find object orientation a little bit challenging. There's a larger gain when the individual functions, so approaches to white box testing have to be extended. So we can have more white box than black box with object orientation because we have to test the interfaces. No obvious top to the system or bottom to the system, so we can't do integration testing the same way. So integration testing provides a few challenges. In terms of the testing levels, we operate with, they're all associated with the objects, which is why unit testing becomes important. And the object classes clusters for cooperating objects, objects working with each other, calling methods upon each other. And then the whole complete system, and you can't get away with that as well. I mean, you have to do the integration testing. You have to do some complete system integration testing. So, in terms of the object classes, this is where you get the JUnit. This is where you get, and if you're not familiar with that, I talked about last time, it's Java. That's code that's written along with the Java source code that's primarily, its only purpose is for testing. And it tests units, but in Java, object-oriented language, the unit is the object class. It's the class. So you're testing the composure of the class, the methods, the behavior. So the complete test coverage of all of the classes involved. In object orientation, you actually have to test every single class. In regular other languages, you don't have to, actually. You can leave some modules alone that their behavior is exposed by the use of other modules and other procedures. For example, like if the print module is broken and the thing's not going to print, if we send something to the printer and it works, we don't have to test it past that usually, because there's connectivity there. But in object orientation, we have a bunch of objects that are all working together, and we may not actually invoke one of the objects. One of the objects might not actually be used in any of the tests, except for in rare cases or something. And in that kind of case, we wouldn't be testing it. If we didn't test it, we wouldn't know if it worked. So testing all the operations associated with the object setting and interrogating all of the object attributes and exercising the objects in all the possible states that they could possibly be in. And if you're in my object-oriented programming course, it states the behaviors, the attributes, the methods, the operations that are being performed is what's essentially being tested here. So inheritance makes it more difficult as well to design object classes to test the information that's going to be tested. It's not localized, it's inherited. So what ends up happening is you run this test and you go, where's this behavior coming from? It's not in this object. It's in an object that was inherited. Oh. So then you have to go through and you have to test all the objects in the tree? No one's going to do that. It's too extensive. It's like testing everything about the source code. It's not really going to be possible. Here's an example using weather station. We have an object interface to it. Here's a class over here, or an object called weather station. Tool identifier. Has some methods in here. Don't worry about it if you don't know anything about object orientation. Just consider this a class. So you have test cases that are needed for all of the different operations or all of the methods that are part of the class. You use a state model to identify the state transitions, which is the state's going to be the identifier. And then you have some examples of the testing sequence down here where you have shutdown, waiting, shutdown. So you go through a sequence of behaviors that occur with one object, and you say, these are the different states that it can be in, these are the different behaviors, the different functionalities of that particular object. And you have to make sure you actually test every one of them. This is why JUnit's so popular, because you write the JUnit test, the unit test for the class, while you're writing the class. And I believe there's an automated tool out there that does it for you. And I think it's part of Eclipse. It works with Eclipse. It's an add-on package. And I hear it's not so reliable, but it does make a nice attempt. What it does is it surveys your code, and it puts together a template of everything you need for it. And then you fill in the blanks and you figure out how to run each one of the test cases. In terms of the object integration, it's the objects working with other objects. The levels of integration are less distinct in object-oriented programs than they are in other types of development environments. In fact, they're probably easier to see from an interface point of view, looking at the objects interface. So cluster testing is concerned with integrating the testing objects, cooperating objects, identifying clusters, using knowledge of the operations of the object of the system to essentially design the tests, to implement the clusters. And clusters is, working with objects that work with other objects, cooperating. So we don't have clusters in cluster concept kind of exists because we have functions that call functions in non-object-oriented programs. But especially with objects, we have a group of objects that all work together to accomplish a task, which would be a cluster. So we have to actually perform cluster testing in order to get that coverage stored correctly. Where'd you guys come from? Like a bus let out or something. Alright, so we have use cases and scenario testing that becomes part of it. So testing is based upon the user's interaction with the system itself. Use case scenarios, we covered that in Software Engineering 1. We could look at thread testing, which we didn't cover, which looks at the system in terms of events, processing threads through the system. That's actually kind of difficult. We don't have any tools for that. usually. This is easy because it's black box testing, the use case scenarios. The object interaction testing, well, that's our JUnit testing. That's our unit level. So all of them are pretty much something that should be taken a look at. In terms of the scenario base, we covered this in software engineering wise, discovering the use cases or the scenarios. By doing scenario planning, we can figure out what result should come out of what and what object uses what other object in terms of a use case. We collect the weather data. We can actually go through, and then this should look familiar maybe. It's a sequence diagram that shows you how the object changes from a request to an output and how it exercises different components of the object. Classic approach to doing a sequence of events, or kind of think of it more like a flow chart, I guess, of the object interactions. And then we have weather station testing as an example, using method or method execution, running each and exercising each one of the methods. This is where I said tools like JUnit, unit testing, looking at the inputs, looking at the outputs, saying this input, this is this output, this is, and comparing it against expected. And a lot of automated tools do this for you quite nicely. So you actually have to do manually. Scenario testing is all done manually. This is done automatically in terms of unit testing. And then the concept of the testing workbenches. So testing is expensive process phase. It takes a long time. If you save it for last, it's never going to get done. Workbenches provide a range of tools to reduce the time required and total testing costs. You get workbenches with your automated testing tools. And some of the software packages out there that are designed for testing. Most testing workbenches are open systems because the testing needs an organization-specific kind of integration or customization. You can't just buy a test workbench, open source, or you can't even, you can't go like off-the-shelf type software package that's going to do your testing for you. You've got to customize it. You've got to make it work with your program and your environment. You put together this suite of tests, call it a workbench, and close it all together, and it becomes a program, or it becomes a process in which you've got testers that are performing this activity, recording results, archiving results, and then you can perform regression testing and a bunch of other stuff from that. It's difficult to integrate with closed design and analysis workbenches. Sometimes the tools don't work together with each other, and they don't basically create the ability to archive or to merge this information in together. But essentially, if you have a good testing workbench together, you can run out statistics and stuff. You can say, well, most of our problems fall here, most of our problems fall there. We've done this type of coverage. We have this type of reliability. And you can come up with a bunch of statistics that come out of the organized testing environment. So here's an example where we've got some source code over here. Dynamic analyzers come in, a little exception report. We got some programs that they're being tested, subprograms, a little test manager, test data. So it kind of like all fits together, flows together in terms of a process. So test workbench adaptation. So scripts, using scripts that may develop for user interface simulators, patterns, test data generators and stuff. So you can kind of automate it, because the worst thing you want to do is kind of exhaust all of your manpower effort to do all of this testing manually, when this can just run overnight. Design a workbench for it, run it, have the computer test it essentially instead of the humans, which may or may not necessarily hold true for most programs. So test the outputs that they may be prepared manually for comparison. So you can actually run your automated testing with your manual testing and see if you get the same results as well. Then you know, because it's kind of like if you build a good program to do it, how do you know the program's actually doing it correctly? And then if the program's not working correctly, you can't trust the results that you're getting. Your testing is worthless, essentially, bottom line. So you have to compare it anyway, do some spot checks on it to validate that the testing is correct. And special purpose file to compare things, can be developed. So, all right, so let me put some summary on this. And next week, I'm actually going to talk about the second part of the last lecture I was talking about last week, which I'll bring in. In fact, this is actually probably a good idea that I did this, because the second part actually hits on a lot of testing issues that are covered in this lecture in terms of integration testing and component and how to do object-oriented type of testing. So we'll revisit those next week when I finish the last week's lecture. But some key points to walk away with in terms of this particular testing lecture: the test parts of the system. You want to test parts of the system which are commonly used rather than those that are rarely executed, because testing is always done as a last resort, ditch effort. Nobody actually kind of sees testing as the most important part, actually, but it is kind of the most important part of the application development process. Equivalent partitions are they're sets of test cases where the program should behave in an equivalent way for a given range of inputs that you might give it. So coming up with your correct, valid partitions that are equivalent is important, so that you know that you've tested the full range and that this input, you don't have to test every single input possible. You can actually have equivalent ranges. Black box testing is based on the system specification, as we've seen. Structural testing identifies test cases which cause all paths through the program to actually be executed. Structural testing is a part of white box, and it also can be used in black box kind of varieties, but it's primarily a white box kind of thing because we're testing the internal structure of the source code instead of the external functionality. And on a side note, that the black box also tests the requirements and the actual features of the system versus the working of the system or the process of the system. Test coverage measures the entire, ensures that the entire statements have been executed at least once. So the term coverage is referring to that you've actually tested the entire program. We've gotten at least something tested for each one of the sequences. Interface objects arise because the specification might be misleading, misunderstanding, there might be errors, or maybe there might be an invalid timing assumption. Maybe it's expecting a network connection to be established and it's trying to do something that relies upon that connection that doesn't exist yet or something. So keeping in mind the timing, misunderstandings, and the interfaces of the objects, and also changing interfaces. Every time you add an upgrade a module, upgrade a library, the interfaces might actually change. Wording, typos, and stuff like that might exist. To test object classes, you test all the operations, the attributes, and the states. We test all the components of the actual physical class that's being created. And we actually have to test everything related to the object, all of the methods, all the states and behaviors that it might actually possess. And we integrate the object-oriented testing around clusters of objects. So we focus on groupings of objects that work together. There's absolutely no need to test this object over here, which never even talks to this object way over here. Only the clusters or the groups that work together are important in that case, which is kind of the same logic you would apply towards functions or procedures, modules. You're only testing what's working with other systems, other components. So. Okay, so that was lecture number 8, and next week we will go back to 7 and finish it, and talk a little bit more about testing, and then we'll move on. In the future, we got feasibility coming up. We've got budgeting, scheduling, estimating, and some of the business aspects of trying to figure out what to charge people, I guess, for software that we might want to build. So. All right, that's all for today. See you next time.